Microtunnelling is a technology established worldwide for installing pipelines without the need for open-cut trenching. For more than 40 years, Iseki have been pioneering and developing this technology, a fully remote-controlled system that works unobtrusively underground. When compared with other methods, microtunneling provides improved site safety, less disruption to both the environment and the community, and has a greatly reduced carbon footprint. Microtunneling machines are designed to perform in all ground conditions, from soft clay to hard rock, with very high accuracy. The end result is a hardy, watertight finished pipeline, achieved with minimal surface disruption. Iseki design, manufacture, hire and sell microtunneling systems and offer operation, maintenance and refurbishment support to suit clients' needs. Our ability to work through a range of diverse ground conditions, environments and locations means we can provide the best possible engineered solutions for microtunneling projects. Our extensive experience and our range of quality equipment allow us to remain at the forefront of trenchless technology. The microtunneling process begins with careful planning. A full site investigation is undertaken, and all aspects of the project are examined to provide a carefully considered and optimum project plan. The first stage of construction is to prepare the drive and reception shafts, usually at manhole positions. Then, the microtunneling equipment is transported to the drive shaft and assembled in position. Equipment consists of a microtunnel machine, hydraulic jacking equipment, operation and power distribution cabins, slurry pumping and separation equipment, and lubrication equipment, as well as ancillary equipment such as cranes and generators. The drive and reception shafts must be long enough to accommodate the tunneling equipment. A concrete base slab is poured to support the tunneling equipment, and a thrust wall is provided where necessary, giving a solid surface from which the pipes can be jacked. Then an entrance sealing arrangement is installed, through which the microtunnel machine and pipes can pass as they enter the ground. And finally, the hydraulic jacking rig is installed. Then the microtunnel machine, the real workhorse of the microtunneling process, is lowered into the drive shaft and onto the jacking rig. Different types of Iseki microtunnel machines are available to cope with a host of ground conditions. Machines are available in a wide range of sizes, in diameters from 250 millimeters to 3.5 meters and beyond. Once the microtunnel machine is aligned on the jacking rig, which has been precisely set to the required line, level and grade, all cables and hoses are connected to the machine, and the complete system is tested. The drive begins with the microtunnel machine being thrust forward by powerful hydraulic jacks, first passing through the entrance sealing ring, then tunneling through the ground on its journey to the reception shaft. Powered by electric motors, the rotating cutter head cuts through the ground. Excavated material is crushed in the head of the machine when necessary and passes into a slurry chamber, where it's mixed with slurry and transported to the surface via slurry pipes. During excavation, a sophisticated earth pressure counterbalancing system is employed. By maintaining a consistent counterbalance pressure on the tunnel face, always between the active and passive earth pressures, ground movements are virtually eliminated. Once the machine has reached a predetermined position, excavation is halted, cables and hoses are disconnected, and the first jacking pipe is lowered onto the jacking rig. The pipe is pushed up to the back of the microtunnel machine, where the two are linked together, often by an adapter ring, and the cables and hoses are reconnected. Then, pipe and machine are jacked forward as the excavation at the face of the machine continues. After the first pipe has been installed, excavation is halted and the jacks are retracted. The next pipe is lowered onto the jacking rig and then pushed forward. This process is repeated until all pipes are installed, forming the permanent tunnel lining. The alignment of the machine and pipe is controlled using a laser-guided steering system. A laser beam, originating from a laser at the rear of the drive shaft and set to the required line, level and grade, is projected onto a target mounted inside the microtunnel machine. An image of the target is captured by a TV camera and relayed to a monitor in the operation desk at the surface. The operator can activate hydraulic steering jacks inside the microtunnel machine as necessary to articulate the front section of the cutter head and alter the attitude of the microtunnel machine. Accuracies of plus or minus 25 millimeters in line and level are typically achieved over an entire drive. As the microtunnel machine nears the reception shaft, excavation is halted temporarily, and if groundwater or soft ground is present, an exit sealing ring is placed on the wall of the shaft. Finally, the microtunnel machine exits the ground into the reception shaft, completing the drive. The machine and equipment are lifted and removed from the site, and manholes are built, ready for project completion. Microtunneling is the perfect choice for deep sewer and pipeline installations. Iseki remotely controlled slurry microtunnel boring machines have been in production for over 40 years. With nearly 2,500 units manufactured and thousands of kilometers of tunnels installed, they're probably the most popular slurry machines in the world. The Uncle Mole range is widely respected for its versatility, ruggedness, efficiency, ease of use, and ease of maintenance. The Uncle Mole machine, with bidirectional and radial motion, has a unique eccentric cutting and crushing action, and with its general-purpose cutter head, is recognized as the complete machine for all soft ground conditions, which range from clays, silts and sands to soft rock. With the introduction of a mixed ground head, the Uncle Mole machine has recently been further developed to deal with medium rock. The Uncle Mole Super Machine extends the operational conditions to include hard rock. It's fitted with a conventional rock cutting head, but this is mounted directly in front of an eccentric crusher. This crushes and grades large fragments and processes soft ground strata through the machine. The hydraulic jacking system provides the thrust required to move the microtunnel machine and string of pipes through the ground. Jacking systems are available in a wide range of sizes, capacities, and configurations, from 100 tons up to 4,000 tons. The hydraulic jacking system is located at the rear of the drive shaft. After a pipe is placed on the jacking rig, the jacks are slowly extended, powered by a hydraulic power pack on the surface. The force of the main jacks and the speed at which they extend is carefully synchronized with the excavation rate of the microtunnel machine. A thrust ring and pipe adapter ensure that uniform thrust is transferred from the jacks to the pipe. Thrust at the rear of the jacks is transferred to the thrust wall through pressure plates. Jacking systems can be either long-stroke jacks, jacking a complete pipe length in one push and normally requiring a longer drive shaft, or, in order to accommodate smaller shafts, short-stroke jacks, together with spacer blocks, and a variety of indexing systems using multiple strokes of short-stroke jacks. These latter two systems achieve the same goal, pushing an entire jacking pipe while occupying a smaller footprint and permitting smaller-sized drive shafts. At some point during a relatively long drive, the required jacking force may exceed the capacity of the main jacking system, or the structural capacity of the pipe or thrust wall, requiring the introduction of one or more intermediate jacking stations, or interjacks, to evenly distribute the jacking load over the length of the tunnel drive. Interjacks are placed between sections of pipe and move forward with the pipeline, but are not activated until their operation becomes necessary. At such time, the first interjack is opened, advancing the microtunnel machine and the front section of the pipeline. Then, the main jacks in the drive shaft are actuated, causing the closure of the interjack, while advancing only the rear section of the pipeline. This is repeated for each interjack in turn for the duration of the drive, and upon completion, the hydraulic jacks are removed and the pipeline closed up, leaving, in effect, standard pipe joints. The slurry system is responsible for performing two functions: to remove the excavated spoil from the tunnel and to counterbalance any groundwater. The slurry system consists of a closed pipeline loop, which circulates a slurry mix through the head of the microtunnel machine, where excavated materials are picked up into suspension and carried out of the tunnel to the slurry separation equipment on the surface. The slurry is pumped through the system by a number of electric pumps. The flow of slurry to and from the microtunnel machine is provided and controlled by a number of variable speed pumps. A pit bypass unit provides the means of disconnecting and reconnecting the slurry lines and of reversing the flow in order to clear any blockages. When excavating cohesive soils, the slurry may be plain water, perfectly suitable to carry clays and silts. In sandy or granular soils, thickening agents such as bentonite or polymers are added to the water to increase its density and viscosity and act as a support medium to carry these denser spoils to the surface. The slurry and excavated materials are separated in stages by a system of solids removal at the surface. This firstly removes gravels and clay balls, then sands and coarse silts, then fine silts and clays. The clean slurry is reused in the circuit, and the spoil is collected in a spoil skip for subsequent disposal. The Iseki slurry system serves a second, very important purpose. Where groundwater is present, the slurry pressure at the face of the microtunnel machine is adjusted to counterbalance the hydrostatic pressure in the ground, thereby eliminating the need for dewatering. This is also a mechanism for controlling movement of granular soil into the shield, thus preventing over-excavation. Pressure sensors in the microtunnel machine measure both the groundwater and slurry pressures, and the counterbalance pressure is adjusted by use of variable speed slurry pumps and a pressure control valve. A crossover system and shut-off valves apply the counterbalance pressure to the face and are also used to suspend flow through the slurry chamber on the introduction of each pipe and at the end of each shift. The jacking force required to thrust the pipeline forward is mainly a function of frictional forces built up around the pipeline. As the length of the drive increases, so does the total friction produced between the pipe and the ground, thus demanding a greater jacking force. To reduce this friction, a clay-based or polymer lubricant, mixed in a lubricant mixer on the surface, is injected into the annulus between the pipes and the surrounding ground. Lubricant is always introduced immediately behind the microtunnel machine, usually through a lubrication port in the machine. For larger machines and longer drives, lubrication ports are also provided at regular intervals through the walls of the jacking pipes to provide continuous lubrication around the pipes. This technique results in a considerable reduction in friction, meaning the required jacking force is reduced and longer jacking lengths are achievable. Iseki's digital control system is a robust, self-contained system that offers complete control over the equipment used during the microtunneling process. An integrated power distribution system means that only an external power supply is required. During operations, a trained operator carefully monitors and controls all aspects of the microtunneling process, from the operation desk within the control cabin on the site surface. The state-of-the-art operation desk displays all data information and controls most microtunneling operations. Operation desks can be provided with fully automated, computer-controlled operating and data logging systems. Electrical power from the power distribution cabin is fed to all equipment, including the control cabin, lubrication equipment, slurry and separation equipment, jacking equipment, and the microtunnel machine and ancillary equipment. The laser target indicates the steering and laser status. Many of the microtunnel machine's operational parameters are displayed on gauges mounted around the laser target. All of this information is relayed back to the control cabin via a closed-circuit TV camera and displayed on one of the screens of the operation desk. Electrical transducers, mounted in various locations, supply additional information to the operation desk to inform the operator of the status of every relevant item of equipment at any time. The Iseki data recording system within the operation desk monitors and records the tunneling operations. A communication link enables this data to be transmitted to anywhere in the world and can provide access to remote support, monitoring, and diagnostics by off-site technicians. Pipes used in microtunneling are called jacking pipes and are thicker-walled versions of trench pipes. Jacking pipes have a female end, fitted with a collar and a thin compressible ring to act as a packer, and a male spigoted end, fitted with a rubber seal. When joined together, a durable, watertight seal is formed. The outside surface of the pipeline is smooth, minimizing friction as it's jacked through the ground, and the compressible packer cushions some of the load between the pipe ends, reducing the potential for local crushing of the pipe material. Concrete, GRP, and vitrified clay are the most common formulations of jacking pipes, although steel and ductile iron pipes are also used. Jacking pipes are available with inside diameters ranging from 150 millimeters to 4 meters, and section lengths from 1 meter all the way up to 12 meters. The unique pipe roof method can be used for economically installing large-section, short-length tunnels. Typical uses would be for constructing underpasses or underground railway stations, where use of a large-diameter tunnel boring machine would be either impossible or prohibitively expensive. The pipe roof method is used to construct a temporary works framework consisting of multiple steel pipelines, which are installed by microtunneling from a movable platform. Since each pipeline is mechanically linked to its neighbors, the framework becomes a long and wide support structure. Dependent on ground conditions, the profile of the framework can be a box or a curved or rectangular arch. Ground is excavated from within the completed framework, which is structurally braced at intervals as the works advance. This creates a chamber within which a permanent tunnel structure can then be constructed. The Iseki pipe roof method provides total security against settlement and ground movement, cost savings over alternative methods, and flexibility of design. Since 1972, Iseki have manufactured nearly 2,500 microtunnel machines, and they have installed thousands of kilometers of pipes worldwide. The microtunneling method is a proven alternative to open-cut trenching and open-face tunneling techniques. It is the ideal solution for minimizing surface disruptions when working beneath congested urban and environmentally sensitive areas, avoiding utility conflicts, lessening the risk of ground movements where there are difficult ground conditions or a high water table, minimizing carbon emissions, and minimizing hazards for workers, traffic, and pedestrians. These reasons make microtunneling the optimum solution for deep or shallow sewers, water mains, oil and gas pipelines, and ducts for power or telecoms cables. Iseki is proud to be a world leader in microtunneling solutions.